I'm delighted to be here. This beautiful building did not exist when I was a postdoc here. We had colloquia elsewhere. So before I start, I'd like to acknowledge the people I've been working with in this general area for several years. Aaron Betcher, Chad Bustard, Corey Cotter, and Josh Wiener and Tova Yost Hull are current or former grad students. John Everett was a postdoc. Corey is an undergrad, and I work with some peers as well. So this has been a rich area, and I know that it's also done here, although different aspects from what I'll talk about. So cosmic rays are pervasive. They're everywhere, and they've been used for a long time to study galaxies. So here's a view of M51. This is the poster child for an ordered spiral magnetic field. So what you see here is the galaxy lit up in synchrotron emission. So this tells us that there are both polarized electrons and a magnetic field here. Don't look too closely at the regularity of this magnetic field. It sort of breaks down. More recently, it's been possible to detect gamma rays from the interstellar medium. And this is a gamma ray contour map superimposed on a CO map. And it shows that the gamma rays are coming from the areas where the gas is dense. These gamma rays are probably produced when cosmic ray protons collide with interstellar atoms, produce pi mesons, which decay to form gamma rays. So if we draw together many lines of evidence that I don't have time to discuss today, we can pick out some salient properties for the purposes of this talk. So I always like to show two views of the cosmic ray energy spectrum. This one shows you what a huge number of different experiments there are that fill in the energy spectrum at different energies using different techniques. And I like to show this relatively cleaned up spectrum because it shows how challenging it is to detect the very highest energy cosmic rays, 1 per square kilometer per year. So the cosmic ray spectrum is a broken power law with these features, difficult to see features, the so-called knee, the ankle. For the purposes of this talk, even though the high energy particles are fascinating in their own right, I'll be talking mostly about the cosmic rays of a few GeV, which provide most of the pressure with a spectrum of this steepness. In our galaxy, cosmic rays are close to equipartition in energy with the interstellar magnetic field, with the radiation field, and with the thermal and turbulent energy in the interstellar gas. Cosmic rays are highly isotropic in their arrival direction, and they seem to be resident in the galaxy for about 10 million years. So we can extend our study of cosmic rays to other galaxies using both synchrotron and gamma ray observations. These are two fits to the gamma ray spectrum of the starburst galaxy M82. So the low energy points are Fermi, the high energy points are Veritas. This was done by my former student Tova. The two views are slightly different because one of them is the best fit to the gamma rays. This one is the best fit to the radio. But what was actually surprising to me is that relatively Milky Way-like assumptions about cosmic ray acceleration, namely that about 10% of supernova energy goes into cosmic rays and that the primary spectrum has an e to the minus 2.1, 2.2, 2.3 spectrum, can actually provide a very good fit in a galaxy which is like the Milky Way on steroids. So the interstellar medium of M82 has about 1,000 times more energy density in all forms than the Milky Way. If we go to really high energy density systems, we start to see a breakdown in equipartition between cosmic rays and magnetic fields, which is sort of a central tenet of many radiosynchrotron observations. So here's a table showing supernova-powered gas density, cosmic ray energy density, radiation, magnetic field energy density, and magnetic field strength. And what I want you to notice is that as we go to more and more dense and energetic environments, the cosmic rays are not keeping up. So here in ARP 220, their energy densities lag far behind the energy density in other forms. And this could be due to reduced efficiency of acceleration, but it's, in our model at least, it's well fit by just putting in the huge collisional losses in a medium of this high density. So you're putting the power into the cosmic rays, but their lifetime is so short that they never build up an appreciable energy density. We can also apply this modeling to the central molecular zone of the Milky Way. So there was a soft gamma ray excess detected a number of years ago and corroborated with other instruments. It's been suggested that this is a signature of decaying dark matter, or more prosaic explanation like pulsar wind nebulae. We tried to see if you can model it with a soft component of cosmic rays, so a diffuse origin, and you can fit the spectrum, but these fits are very problematic. So if we posit a population, sort of an extra electron population, it way overpredicts the synchrotron radiation by many orders of magnitude. And if we posit a soft proton population, you need to put several hundred times more energy into that population than you do into the rest of the cosmic rays. Since we're already using 10% of supernova energy for cosmic rays, that's just untenable. So the loss rate, so we include collisions, and they're actually very important for secondary electron and positron production, but we also include advection as a parameter that we fit. Okay, so what you've just seen is basically some of the collisional coupling of cosmic rays to the thermal gas. So they're important for ionization, for heating, for chemistry, radiative processes that you've just seen, and also light element production. So the lithium that we see is created in the interstellar medium. But there's also a collisionless interaction in which momentum and energy are exchanged with the background gas mediated by the ambient magnetic field, and that's really the subject of this talk. And here, so we can sort of think of the founding fathers of this discipline, Fermi, Gene Parker, Russell Kulsrud, kind of being the primary particles and creating this air shower of secondary researchers, of whom I am one. So this is an active subject. Okay, so in this talk, I'll try to motivate studying this energy momentum exchange. Then I'll talk about the theory which is most often used or approximated, which we can call classical cosmic ray hydrodynamics. And then I'll generalize classical cosmic ray hydrodynamics and, among other things, attempt to provide a justification for some of the more approximate treatments in literature. And this will be partially but not completely successful. And then we'll go beyond Alfven waves, which various researchers have also invoked for a variety of reasons. And this basically means considering very extreme parameter ranges. And then I'll say a little bit about the unfinished business in the subject and conclude by telling you should all work on cosmic rays. Okay, so galactic winds. So this is a very simple sort of introductory motivation. So these are two flows from a spherically symmetric galaxy with a simple gravitational potential. They're thermally driven. They have the same central temperature, but the blue lines correspond to a gamma equals 5/3 gas, and the red lines correspond to a gamma equals 4/3 gas. And you can see that a gas with a relativistic equation of state cools more slowly, and it drives a faster wind. So, and we will continue to see this in more complicated models. So, to kind of foreshadow, we applied this classical cosmic ray hydrodynamics model to a wind from the inner Milky Way. So the idea was to fit these soft X-ray observations with ROSAT. We made a very simple one-dimensional flow model with very idealized magnetic geometry. Because it was a simple model, we could run tens of thousands of them and kind of scope out this parameter space for what best fits the observation. So here's gas pressure, cosmic ray pressure, mass loss rate, and you can see that the best fit model has about equal cosmic ray and magnetic field driving. The cosmic ray driving includes both the pressure gradient and the collisionless heating, which I'll explain. And you can see the effect of leaving in cosmic ray heating or turning it off on the temperature in this wind. So it's quite important in addition to the direct momentum driving. Okay, so recently we've gotten a little bit fancier. These are some preliminary results comparing two model disk galaxies in which star formation is occurring in sort of a cookbook way with, when gas goes above a certain density threshold. There's an initially toroidal magnetic field in the disk, and the star formation, greatly disturbs the galaxy. So this is gas density on both, but there are no cosmic rays in this model. And here we assume that 10% of energy goes into cosmic rays from the supernovae, and boom, we get this huge wind. So we think, and we're not the only ones to think, that so-called cosmic ray feedback can be very important in the evolution of galaxies. It can drive outflows much more efficiently than thermal gas alone.
Before you move on, though, can you just tell us a little bit more details of what's included on the right-hand side in terms of the wind?
Yeah. So we have a certain fraction of energy going into cosmic rays, and it's both. We have fully implemented the classical cosmic ray hydrodynamics, which I'll describe. Okay. So how does this coupling occur? So this is basically a collisionless system. So the perpendicular dynamics are easy. The cosmic rays have no inertia. They satisfy a sort of perpendicular force balance where their perpendicular pressure gradient, Lorentz force, crossed with B. The Lorentz force on the thermal gas is the current in the gas cross B. Of course, we don't want to actually decompose these currents, so we use the combined current, J cross B, which is the curl of B, so easy to calculate. And using these two, the perpendicular cosmic ray pressure gradient shows up as a force on the thermal gas. So this may seem like a trick, but it's basically true. JC is the current carried by the cosmic rays, and JG is the current carried by the thermal gas. And of course, we don't know how to separate them. But if we add them, we can just use Ampere's law. Yeah, that's a good question. So a priori, not necessarily, but when we go to this frequent scattering picture that justifies a fluid approximation in the first place, it will seem to be a good approximation. But there are situations where it wouldn't be. So in a medium like the Milky Way, probably, there are situations where you definitely would want to include energy loss terms in the cosmic ray energy equation, and cosmic ray propagation codes like Galprop actually do that. But cosmic rays I think they're only really dynamically important in situations like the Milky Way where they're relatively lossless. Okay, so that was the perpendicular dynamics, one slide. The parallel dynamics are a little more subtle, and I'm going to ask for your patience in going through them. Okay, so the sort of foundational idea is this gyroresonant scattering. So here's a magnetic field line with large-scale curvature and tiny-scale structure. That's the thing in red. And here's a particle with a gyroradius that's kind of intermediate between the large-scale curvature and the small-scale wiggles. And just as you can successfully ride your bicycle up and down over lengthy hills and just hurt your hands a little bit if you go over washboard pavement, the cosmic ray successfully follows the field line. But if the gyroradius and the scale of variation are the same, that is a resonant interaction, just like going over a bump on the road which is about like the separation of your bike wheels, and there's a large response. So here's an integration of a resonant interaction, and here's a non-resonant interaction. The resonant interaction is obviously much bigger. So this is the basis for the gyroresonant streaming instability, one of Russell Kulsrud's many contributions to the field. And it has a growth rate, which I want to show you because it'll become a little more important later. So this is the condition of resonance, cyclotron frequency, parallel velocity, k vector. Mu is the cosine of the particle pitch angle, as defined on the last slide. This factor, since the cosmic ray distribution function is a decreasing function of momentum, provides some damping, a negative gamma, but a sufficiently large anisotropy will destabilize these waves. And you can write the growth rate in kind of a simple form like this. The gyro frequency times the ratio of the cosmic ray density to the thermal plasma density times the ratio of the drift anisotropy to the Alfven speed -1. And I'm interested here in kind of the bulk cosmic rays with a gamma of order 1. Okay, so we can find the back reaction of the cosmic ray wave interaction on the zero order distribution by so-called quasi-linear theory, which is averaging the Lorentz force produced by the waves acting on the first order distribution, assuming that these interactions are small, that the waves are nearly periodic, and that they're randomly phased. And you can show that this interaction takes the form of diffusion in momentum space. And this diffusion, because the speed of an Alfven wave is much less than the speed of light, is primarily an elastic scattering in the angle of propagation. And the scattering frequency is of order the cyclotron frequency times the relative power in the magnetic field fluctuations. And the momentum terms in the diffusion tensor are of order VA over C or VA over C squared. So it's a primarily elastic scattering, but not entirely, otherwise there would be no energy transfer. So we can derive an energy equation by multiplying that Fokker-Planck equation by the particle energy and integrating over momentum space. And here's the energy density, here's the energy flux, and this is just the energy transfer to the waves. So what this says is that there's energy exchange between the waves and the cosmic rays. In the absence of waves, the cosmic rays would conserve energy the way a fluid normally does. Okay? We can take this a little bit further, make it more useful, if we assume that the scattering is frequent. In other words, that the mean free path for scattering is much smaller than the kind of class characteristic scale of the system. And then we can relate the anisotropy in momentum space to the density gradient. And then, putting all that back in and doing some more manipulations, we can get a very simple form for the energy equation. So here's the same left-hand side. And on the right-hand side, we have this term, the Alfven speed, dotted with the cosmic ray pressure gradient. And this looks like frictional heating. Okay. Or at least frictional energization of the waves. So now let's look at an equation for the waves. So many years ago, an equation for wave energy density or action density was derived by Dewar. And this is sort of the adiabatic part. And Chris McKee and I worked with this many years ago to derive kind of an equation of state for Alfven turbulence in molecular clouds. But now we're interested in the cosmic ray piece. So there's driving and there's dissipation. And in equilibrium, they must balance. And because the energy density in waves tends to be relatively small, these are generally the two dominant terms. And we can identify them with a heating rate. Okay, so this is the basis for classical cosmic ray hydrodynamics. These equations were first developed, I think, by Heinz Folk and his collaborators to study how cosmic rays would back react on shocks. So this was sort of the first refinement of the theory of diffusive shock acceleration. And the key ingredients are that they stream down their own pressure gradient at the Alfven speed relative to the thermal gas. Now, this is actually not easy to implement because if the Alfven speed has some sort of minimum, like if you're going from a low density region to a high density region, so the Alfven speed slows down and the cosmic ray pressure tends to build up. So then you have this paradoxical situation where cosmic rays are streaming up their density gradient and interacting with waves. This is kind of counterintuitive, and John Skilling showed a long time ago that what actually happens is the cosmic ray profile flattens out. I was always kind of skeptical of these arguments, but they've been shown now in a numerical simulation by Josh Wiener at UC Santa Barbara. So you need some care in making sure that cosmic rays are only coupled to the gas when they're streaming down their density gradient. Pratik Sharma, a former student here, found a nice way to do that, which we've implemented. So when they're streaming down their pressure gradient, they transfer momentum. The grad P force acts. And then they heat the gas in this way I just showed you, VA dot grad PC. And they diffuse along the magnetic field, not across the magnetic field, with some diffusivity which you can calculate. Okay. So this has been applied to shocks, to galactic winds, to heating the interstellar medium, and to heating the intracluster medium, and it's also been applied to propagation. So where do the cosmic rays go, assuming where they're generated? Okay. But this is kind of difficult and involved, and so various approximations and improvisations have been made in the literature. So one way of doing it is to include the cosmic ray pressure gradient force and assume that the cosmic rays are advected with the fluid. So not at the Alfven speed relative to the fluid, but with the fluid itself, to ignore the heating and to put in some sort of anisotropic diffusion, if you put in diffusion at all. So this has some advantages. So one advantage is that you don't actually have to calculate the magnetic field. So the magnetic field doesn't appear anywhere in the calculation. You just kind of assume it's there and it's providing some coupling. So this simplifies things. If there's diffusion, if there's isotropic diffusion, you are sort of implicitly assuming that the magnetic field is stochastic on the scale of the gyroradius, which allows cosmic rays to wander from one field line to another. You don't need to worry about the streaming being down the cosmic ray pressure gradient because you don't know where the magnetic field lines are. Okay, so this has been used by various groups. And another approximation that's been used is to include the streaming relative to the thermal gas and include the frictional heating, but replace the Alfven speed by some other speed. And the most popular candidate is the thermal sound speed. And this has the same advantages as this. You don't have to calculate the magnetic field. Don't have to worry about where the field lines go. It's a much simpler way to treat the problem. So these are the main variants in the literature. And what I want to do now is see if there's any physical model that underlies them. Okay. So in the sort of infancy of this theory, not too much was known about interstellar turbulence, and the theory is restricted to waves that the cosmic rays generate themselves. But there are other sources of turbulence. This was actually recognized long ago for the high-energy cosmic rays. Here's a simulation of MHD turbulence by my colleague Stas Boldyrev at Wisconsin. Long box. You can see that the turbulence tends to kind of, so there's a strong magnetic field in this direction along the box, and you can see that a lot of perpendicular structure builds up, and it's a very kind of rich-looking picture. So what if we went back and generalized the Fokker-Planck equation to include waves traveling in both directions, waves provided by some other source of turbulence? What would happen if we did that? Well, many sheets of paper later, we would find that the cosmic rays are streaming with a kind of composite velocity, which is like the weighted mean of the Alfven speed weighted with the frequency of collisions with forward-going waves and the frequency of collisions with backward-going waves. So if you have the same wave intensity traveling up and down the magnetic field lines, the cosmic rays are not advected relative to the fluid. And if you have only one sign of wave, then their speed is either plus or minus VA. And the pressure gradient force is unchanged. So colliding with any form of wave will transfer some momentum. So the wave evolution equations, we can modify them to include some sort of extrinsic driving. We keep the damping. This is either excitation or damping by the cosmic rays. This stuff is as before. And we can make a very simple model by, again, just balancing the driving and the damping. For convenience, I've introduced this Alfven streaming time. And then we just have a pair of equations. So I'm assuming that waves are damped at the same rate, gamma for amplitude, and that they're driven in equal amounts in both directions. This is a very simple model to solve. And if we do that, we find that everything just depends on a single parameter, which is like the ratio of extrinsic driving to cosmic ray driving. And the streaming velocity is the Alfven speed divided by this. If you turn off the extrinsic driver, you just get back to the Alfven speed. And if the extrinsic driver dominates, it's essentially 0. So because the heating rate is W dot grad P, the actual cosmic ray heating is greatly reduced when this happens. But, and now this is between sort of you and your confidants, maybe you should put in turbulent damping, and that compensates. And so it's not clear that the amount of heating delivered to the gas is actually reduced in this model. So to summarize the extrinsic turbulence model, cosmic rays are advected at the fluid speed in the limit of very strong external driving. Cosmic ray heating is negligible. Again, you can think about whether you want to include turbulent heating. The pressure gradient force remains. So this is all consistent with a model in which you have some sort of strongly driven balanced turbulence. Balanced meaning it is the same in both directions. Diffusion is a little more complicated because Alfven turbulence produces anisotropic field-aligned diffusion. And to get isotropic diffusion, you have to assume that there's some sort of small-scale stochastic field which the cosmic rays wander around in space. But still, this is a viable model if you have a source of Alfven turbulence. Well, that's through the pressure gradient force. So the pressure gradient force is just the momentum transfer, I think, between the cosmic rays and the waves. Yes. Sorry, what's the entropy? Yeah, so the cosmic ray heating is, it's the pressure gradient dotted with the relative velocity between the cosmic rays and the fluid. That goes into heat. If you assume that, because that is the driving term of, that's the driving term for the waves, and if you assume that driving is balanced by damping, then the damping, ion neutral friction, whatever, goes into heat. Sorry, assume what? Not necessarily. So you can put in a spatial diffusion, and if you have significant spatial diffusion, that will smooth out the cosmic ray pressure gradient. So the heating in that sense, the heating, the pressure gradient force, whatever, will be less due to diffusion. But that doesn't appear as any kind of additional speed. The speed is... Well, it's not... It's it's not really adiabatic in the sense that cosmic ray energy is going into waves, and the waves are damping on the background. So there is actually heat. There is actually entropy production by the cosmic rays. Yeah, so that's right. So that's taken into account in the streaming part. So there's this speed, relative speed, and so if you compress the fluid, if the cosmic rays are locked to the fluid and you compress the fluid, the cosmic rays will be, yeah, their pressure will increase like a gamma equals 4/3 gas, and that's in the theory, but that's distinct from the dissipation. Okay, no. And I guess I can also say, if we go back a little bit, that that we actually did include these terms in a model that we made of cosmic ray propagation into a cloud. So you can do that. You can keep everything in, but these terms are small and they tend to just give you boundary layers, and this is really the dominant balance. Okay, so where are we? That was the extrinsic turbulence model. Okay, so is it always Alfven waves that we should be interested in? So this is, oh, sorry, I didn't put the credit on. This is actually a figure from one of Russell's papers. This is what happens to Alfven waves in a very, very high beta plasma. So this is a plasma in which the gas pressure is much, much greater than the magnetic pressure. I think in these figures, it's 1,000 times greater. Why would we be interested in this? There's very little going on in the diffuse universe, interstellar medium, galaxy clusters, where the plasma beta is actually that high. But in the early universe and in the general intergalactic medium at large, could well have been. So what happens? How do cosmic rays interact in that situation? So what happens is, so down here, this is kind of the Alfven wave branch. This is a scaled wave number. And what happens is that the two different circular polarizations drastically diverge. One of them becomes this is called the fast mode, and one of them becomes a slow wave. And it actually asymptotes to a constant frequency with 0 group velocity. And cosmic rays that interact with waves like this will try to be driven down to the speed of these waves, which is extremely small. So which waves are affected, or sorry, which cosmic rays are affected by this type of wave? Well, it's waves with, oh, this should be less than mu, pitch angle less than this critical value. And this is the ratio of the ion thermal speed to the speed of light times the square root of the plasma beta. So if you look at this, for example, in galaxy clusters, so a temperature of maybe 10 kilovolts and a density of 10 to the minus 3, this requires that the magnetic field be less than about 10 to the minus 12 Gauss. Now we think that magnetic fields in galaxy clusters are sort of in the microgauss to 10th of a microgauss range. So this doesn't apply to galaxy clusters as they are today, but it might have applied to galaxy clusters a long time ago. So what will happen? So I think in contrast to cosmic rays streaming at some very high speed, they're actually constrained to stream at a very low speed. Sort of the opposite way to what was assumed. Now, there is another class of instability which maybe does more like what you intuitively think it should do. And these are sometimes called Bell instabilities, and they kick in when the cosmic ray energy density, the ratio of cosmic ray to magnetic energy density, is much higher than the ratio of the speed of light to the streaming speed. So this requires an extreme imbalance between cosmic ray and magnetic energy density, an imbalance that we actually don't know of anywhere in the universe except in diffusive shock acceleration, so young supernova shocks. So you can kind of, this is the plane. This is just a cartoon, doesn't have numbers in it, but this is the magnetic field strength cosmic ray flux plane. And if we go to the upper half of the plane is where the magnetic field is too large for these non-resonant instabilities. So that's up here. But as you go to higher and higher cosmic ray fluxes, you need a larger and larger magnetic field to satisfy that condition. Then there's this sort of thin wedge where the kind of classical, it's hard to call something classical that's only 10 years old, but classical instability operates. And then down here, the thermal effects become important, and they modify this instability. But as you'll see in the next slide, they don't entirely eliminate it. So, so this instability could exist as well as in young galaxies as well as at shocks. And so here are the growth rates. This is a set of plasmas of different temperatures. This is a 10 to the 7, 10 to the 4, 10 to the 3 degree plasma. This is frequency in, actually it's physical units, and the wave number in inverse cosmic ray gyroradii. And you can see, so the resonant instability is down here, and the non-resonant instabilities are up here, and they grow very fast. And so this is actually one of Anatoly's older simulations, but what it shows is that the instability grows very rapidly to nonlinear amplitudes. It creates these filaments of magnetic field and current, which are very interesting, but not really amenable to the kind of analysis that I've described. Why are they not amenable? Because these instabilities have very large, the real and imaginary parts of the frequency are comparable, and all this sort of quasi-linear diffusion formalism that I described is not really adequate to deal with that case. So far, we only have simulation that deals with that case. So if you're in a situation where either the plasma beta is enormous, very weak magnetic field, or the flux of cosmic rays is extremely large and or relative to the magnetic energy density, there are these rapidly growing small-scale magnetic fields, which I think could be very interesting in weak field situations, but we don't really know, or we don't really have an analytical handle, at least, on how they heat plasma, what the sort of long-term evolution of these things is. They're very interesting, but I think the application of them to anything but supernova shocks is really in its infancy. So that's kind of a frontier for the future. Okay, so summary. So cosmic rays really appear in diffuse plasmas everywhere, energetic particles. And their existence really is in defiance of thermodynamics. Because think about it. In the interstellar medium, one particle in a billion is a cosmic ray, but they have as much energy as the rest of the thermal plasma combined. This is extreme income inequality in the interstellar medium. So there they are. And they exchange momentum and energy with the background, mediated by the magnetic field. And this is a great time to be studying cosmic rays, because the observations, the computations, experiments, which I didn't talk about, they're just all multiplying, and this is a wonderful time to study cosmic ray acceleration, transport, and feedback. And we have, I think there's a good case that cosmic ray feedback is important in the early stages of at least some galaxies, and that it's got to be treated properly. So, thank you.